This time I'm going to hit it with full phasers at point-blank range.
Sensors show the object's hull is solid neutronium. A single ship cannot combat it.
Neutronium, the fantastic material of the Star Trek Doomsday device. Now there's just one teensy problem with making a starship out of neutronium, and that's that it's one of the most powerful explosives that we know of. You see, it breaks down like this. We're all made up of atoms, which are these sort of fairly big electron clouds. And if you zoom right in, what you find is in the middle of that, there's this really small, really dense nucleus, which is typically made up about 50% of protons, 50% of neutrons, and it's really dense. Now what neutronium is it's a material made up entirely of neutrons, so it's incredibly dense. In fact, the only place that we know it exists in the universe is in neutron stars. Now I know a lot of you will be asking and be saying, hang on, didn't you just tell me that neutronium was like one of the most powerful explosives in the universe? And then you also just told me that neutron stars are made out of neutronium, but neutron stars don't explode, so what's the deal? And didn't you also tell me that I'm 50% by weight neutrons, and yet I don't explode, so what's the deal? Well, yeah, that's right, your body is made up about 50% by weight of neutrons, but all those neutrons are actually in the cores of nuclei, and when they're there, they're held together by this really short range and really strong interaction, inventively named the strong interaction. And that means that when the neutrons are in the nucleus, they're really stable, but if you get them outside of the nucleus, they decay typically in less than 10 minutes, and when they do, each one releases about a mega electron volt of energy. Now that won't mean much to a lot of people, so let me translate this into something a little more graphically accessible, like say for instance, tons of TNT. So for a normal person, about half of your body weight is neutrons. So let's just say, for sake of argument, about 50 kilos of neutrons. If I were to wait for all of these neutrons to decay, they would release the equivalent energy of 1 million tons of TNT. That's a megaton of TNT. Now at this point, I should stress that this wouldn't be quite like a regular explosion, where virtually all of the energy is essentially released instantaneously. You see, once you actually get a neutron outside of the nucleus, it has a half-life of about 10 minutes, which means that in about 10 minutes, half of your neutrons will decay and release their energy. Now, a few little calculations later you can show that what this in practice means is that in the very first second, you will release about 1/1000th of the total energy. So what this in practice means is that if you were to get your neutron separated self, in the very first second, they would release the equivalent energy of 1,000 tons of TNT. And in the first 30 seconds, they would release about the same energy as the first nuclear weapons. So what about neutron stars, I hear you ask? There's no strong interaction with the protons there keeping the neutrons stable. Why don't they decay? Well, yeah, that's true enough, but there is gravity and a whole lot of mass. The entire star compressed into something about the size of Manhattan. And it's that immense gravity, this immense pressure, that actually stops the neutrons in neutron stars from decaying. But of course, that's only true as long as the neutrons are actually in the neutron star. If you could extract some of that neutronium from this really high pressure environment, it would be a different story altogether. So there it is. Finest grade neutronium suspended in both an anti-gravity and a stasis field, for good reason. You see, this 1 cubic centimeter of neutronium weighs about 1 billion tons. Now just to put that into perspective, there are about 1 billion cars on this planet. 1 billion cars. And each one of them weighs about a ton apiece. So this 1 cubic centimeter of neutronium weighs about the same as all of the cars on this planet put together. Or another more human way of looking at it, there are about 7 billion people on this planet, call it 10, and they weigh about 1/10 of a ton apiece, which means that this 1 cubic centimeter of neutronium weighs as much as all of the people on this planet put together. And it's a good thing it's held in an anti-gravity stasis field, because if it wasn't, it would fall straight through my hand, straight through to the middle of the Earth. I mean, just ignoring the pressure considerations for a second, the reason I don't fall through to the middle of the Earth is mostly because of the electromagnetic force. That is, the repulsion of the electrons in myself and the electrons in the ground. However, there is none of that with neutronium, and neutrons interact only very weakly with matter, so it would just fall straight through my hand and just keep going. But that's nothing. I mean, you'll recall that just the neutrons in your typical human would release the equivalent energy of 1,000 tons of TNT every second. Well, this isn't 50 kilos. This is 1 billion tons of neutrons. I mean, maybe the best way to put this into perspective is in terms of the largest man-made explosion ever, the Tsar bomb, which exploded with the
equivalent of 58 million tons of TNT, or all the explosives used in World War II, multiplied by 10.
Well, if the stasis field would fail on this guy, it would release the equivalent energy of 15 million Tsar bombs in the very first second. And in the second second, it would release the equivalent energy of 15 million Tsar bombs. And so it would continue for the second and the third and the fourth second. And it would only be after about 10 minutes that the energy release from this 1 cubic centimeter of neutronium would subside to the point where it was only releasing the equivalent energy of 7 million Tsar bombs every second. So yeah, neutrons, some fairly funky particles, and while there's this awe of the sheer energy of the matter we're made of, neutrons have other properties too. Indeed, in the very next part of this series, we're going to be using neutrons to examine some of the structural properties of life itself.